Let's go. Here we go. Chapter 2, Lesson 17. This does not include anything new. This is a recap of all the other lessons. Remember, I don't go over everything in a lot of detail. I'm just going over the key points. So if there's anything you're unsure of, look back at these individual lessons. This is just really what you may want to use before the exam to make sure there is nothing you have forgotten. Although, if there's anything you're unsure of, as I said, look back at the individual lessons. We started off this differentiation chapter looking at differentiation from first principles. What is that all about? Well, it's looking at the gradient of a curve at a certain point, or the gradient of a tangent to the curve at that point. How could we get the gradient of the tangent? Well, what we can do is we can take 2 points on the curve. So we've got an x and then f of x. If we add on h to x, well, we'd have x plus h as the x coordinate, and then whatever x plus f of x plus h would be. We can work out the gradient by doing y2 take y1 over x2 take x1, so f of x plus h minus f of x divided by x plus h take away x. If you do that, then you will end up with this fraction here. You will end up with f of x plus h minus f of x divided by h. However, what you'll notice is that as this point B gets closer and closer to point A, in other words, as the distance h approaches 0, well, the gradient of the line between A and B will approach the gradient of the tangent. This formula here is known as differentiation from first principles, and you need to, in advanced higher, know how to use it. You will be given a function like f of x equals 3x squared, and you have to differentiate from first principles. To do that, what you want to do is you want to work out this part first of all. So you'll have f of x, work out f of x plus h. So wherever you see an x, replace it with x plus h as we do here. Multiply out the brackets and simplify. Then work out this bit that I've put around in blue, so f of x plus h minus f of x over h. That will give us 6x plus 3h. But what we want to do is we want to think what happens as h tends towards 0. And as h tends towards 0, well, h will tend towards 0 for the 6x plus 3h. And as h is getting towards 0, you're multiplying 3 by some number that's almost 0, so really that's going to disappear. It'll be very close to 0, leaving you with 6x. And that there will be your answer. So this is differentiation from first principles. As I said, in advanced higher, you just need to know how to use it. Here is another example, and there are a few more in that lesson. But as I said, you've got f of x, work out f of x plus h, then work out this fraction part, f of x plus h minus f of x over h. And then from there, think what happens as h tends towards 0. Basically, any term with an h in it will disappear. So that will disappear, and it will leave you with the 15x squared. After that, we looked at the product rule. What is the product rule? Well, apart from being Fiona Butcher's favourite thing in the entire world, it is used when differentiating two functions that have been multiplied together. So in other words, the product of two functions. Here you can see you have 3x squared times sine x. So we're multiplying one function in terms of x times another function in terms of x. So we need to use the product rule. The product rule of y equals u dot v are going to both be functions in terms of x. Well, dy by dx will be u dash v plus uv dash, where u dash is differentiating u with respect to x, and v dash is differentiating v with respect to x. Some examples with that. What you need to do, if you have y equals, for example, x cubed times sine x, well, you would write down u and v. So u would be x cubed, v would be sine x, and you would differentiate both u and v with respect to x. From there, you can use your formula. Say it with me, u dash v plus uv dash. And if you sub in, you'd have 3x squared times sine x plus x cubed times cos x. Take out any common factors because it may help you later on if the question was a bit trickier, except that one is really easy. Other examples, it does start to go on and get a little bit harder. Here again, you've got a function in terms of x. We've got x take away 1 all squared. And we're multiplying that by another function in terms of x. 5x take away 4 cubed. Danielle, what do you use? Product rule! Yes, product rule, because it's the product of two functions. So you'd have u and v. Work out u dash and work out v dash. Just remember the chain rule. The chain rule pops up all the time in advanced higher. So you bring the power down, you take one off the power, you leave the brackets as they are. Differentiate what's inside the brackets and multiply by that. So you're linking outside and inside. It's a chain rule. So you'd get 15 bracket 5x take away 4 squared. From there, u dash v plus uv dash. Work that out. And again, once you get to the likes of this stage, don't start multiplying out all the brackets. You'll need about 37,000 bits of paper. What you should do is look for any common factors. So you've got an x take away 1 here and here. Take out that as a common factor. And you've got a 5x take away 4 squared, which is also a common factor. Check what that leaves you with. Multiply out any brackets. And then you will get down to a nice answer. Lovely. After that, we looked at the quotient rule. What is the quotient rule, Callum? Good. The quotient rule is used when you're dividing one function in terms of x by another function in terms of x, and you want to find the derivative, such as 3x over x plus 4 or cos x over x squared. We've got a function in terms of x divided by another function in terms of x. Your quotient rule then is if y equals u divided by v, well, dy by dx would be u dash v minus uv dash. Notice how the plus from the product rule changes to a minus in the quotient rule, and you would divide that then by v squared. So u dash v minus uv dash over v squared. Again, we applied that to quite a few examples. If you're unsure, look back at the individual lessons. But for this one, we had 2x over x squared plus 1. So we had the function at the top, that was u. So that's 2x, and v is the function at the bottom with x squared plus 1. Differentiate u with respect to x and you get 2. Differentiate v with respect to x, you get 2x. From there, the quotient rule, say it with me, u dash v minus uv dash over v squared. And that will give you 2 times x squared plus 1. Take away 2x times 2x over x squared plus 1 all squared. From there then, you can multiply out brackets, you can simplify, you can factorize, and you will get your answer. Other ones here, again, it gets slightly harder here because you've got the x squared plus 1 in brackets to the power of 4. So when you're doing that, if you're differentiating, that will be u, you'd have to apply the chain rule. So the 4 will come down, the brackets will stay as they are, the 4 will decrease to a 3. You've differentiated outside the brackets. Differentiate inside, you get 2x and multiply together. So you get 8x bracket blah blah blah. For v, that's always at the bottom, so that'll be x cubed. Differentiate that with respect to x, and then we've got again u dash v minus uv dash over v squared, and you can sub everything in there. Take out any common factors. Again, once you get to this stage here, don't start multiplying out brackets. Factorize. If you factorize, you'll get something here in the brackets which will be quite simple. Multiply out brackets, simplify it, and you get down to a nice answer. After that, we then looked at trig functions, so we were introduced to 3 more. We already know that sin x divided by cos x is tan x, and we were introduced to 1 over sin x. 1 over sin x is known as cosec x. 1 over cos x is known as sec x. And 1 over tan x is known as, well, tan is sine over cos, so 1 over tan will be cos over sine. That's flipped, and it's known as cot x. From there, you could evaluate the like of cosec pi over 3, sec pi over 4, and cot squared pi over 6. Look back at the lesson on this, lesson 4, if you want me to explain that. But really what we need to do is we need to differentiate sine, cos and tan and cosec, sec and cot. And this is given in the exam. You are given this, so you know already sine, if you differentiate it, you get cos. Cos differentiate, you get negative sine. Tan differentiate, sec squared. Cosec x, differentiate that, you get negative cosec x cot x. Differentiate sec, you get sec x tan x. And differentiate cot, you get cosec squared, negative cosec squared. And remember, in advanced higher, you use radians, okay? You're always using radians. If we have to differentiate then the likes of tan 3x, first thing you want to think about is tan of 3x means the tan of the whole thing, the whole of 3x. So you'd have to use your chain rule. From there then, you're thinking differentiate outside the bracket. So tan, if you differentiate it, you can see here you get sec squared. So that'll go to sec squared 3x. The brackets just stay as they are. But you have to multiply by the derivative of the bracket. So you're multiplying by the derivative of 3x. Differentiate 3x, you get 3. So you'd multiply by that and you would get your answer. There were quite a few examples on this, but again, we worked our way up to some harder examples. For this one here, example 5, we had to differentiate y equals x to the power of 4 sec 2x. But what do you notice about this one? Well, it's the product rule you're having to use. We've got x to the power of 4 times sec 2x. So you're thinking product rule, u dash v plus uv dash. So u is going to be x to the power of 4 and v will be sec 2x. Differentiate x to the power of 4, dead easy. Differentiate sec 2x. Well, sec x, if you differentiate it, goes to sec x tan x. So because it's sec 2x, we'd have sec 2x times tan 2x. However, it's not just sec x, it's sec 2x. So think about that in brackets. You have to differentiate outside the brackets. So sec will go to, but you multiply by the times where this times 2 comes. The chain rule, the chain rule, the chain rule, the chain rule. Remember that. So we'd have 2 times sec 2x tan 2x. U dash v plus u. Work that out, and you get your answer. After that, we then moved on to look at e to the power of x. We can differentiate e to the power of x, and it's probably the easiest part of the advanced higher course. If you differentiate e to the power of x, you are just left with, Piper, e to the power of x. Perfect, you're left with e to the power of x. Except, what do you have to remember? Chain rule. Yes, you need to remember the chain rule. E to the power of x, if you differentiate it, you get e to the power of x, but you need to multiply by the derivative of the index. For example, if you have y equals e to the power of 6x, well, that would stay as e to the power of 6x when you differentiate, but you multiply by the derivative of 6x. And if you differentiate 6x, you get 6. So you multiply by 6. We'd have 6e to the power of 6x. There were quite a few examples there, and again, we built up to some harder examples with this one, y equals x squared over e to the power of 2x. Ethan, tell us what you use. It's the quotient rule. You got it. Good. From there, u is going to be at the top, that's x squared. V is at the bottom, that's e to the power of 2x. It's one function in terms of x divided by another function in terms of x, so you know it's the quotient rule. Work out u dash and v dash, and then we just have u dash v minus uv dash over v squared. Sub in all the values and simplify, take out any common factors and so on. Note here, if we've got an e to the power of 2x divided by e to the power of 4x, well, that will become 1 over e to the power of 2x. From there, we looked at differentiating our natural logarithm, ln x, and to do that, if you differentiate ln something, it just goes to 1 over the something. So ln x goes to 1 over x. But once again, you need the chain rule. You have to multiply by the derivative of what is in the brackets. So here we've got y equals ln 3x take away 1. So ln something goes to 1 over something. So differentiating that, we'd have 1 over 3x take away 1. But we need to multiply by the derivative of what is in the bracket. So we differentiate with respect to x, the 3x take away 1. Differentiate that, you get 3. So we'd have the 1 over 3x take away 1 times 3. And that will be the answer. Once again, there were quite a few examples, and we built up to some harder examples. Patrick, for this one we're using product rule. Perfect, product rule, because we've got a function in terms of x times another function in terms of x, so it's product rule. U is x cubed, v is ln x, differentiate u, differentiate v, and then we've got u dash v plus uv dash. Take out any common factors and you'll have your answer. We then moved on a little more to look at still differentiating ln x, but sometimes we have to apply log rules before we differentiate. These are your log rules from higher. Ln ab equals ln a plus ln b. Ln something divided by something is ln a to take away ln b. And if you have ln a to the power of n, bring the index down, whee, ba-dump, and you'd have n ln a. Differentiating then, we've just done that, and you can apply your log rules. For example, here we've got y equals ln, and then in brackets, x to the power of 4, e to the power of 2x. The first thing that you would have to do, Alina, is apply your log rules. Good, so we'd have ln x to the power of 4 plus ln e to the power of 2x. Again, apply the log rules. Look at this rule at the bottom here. If you have ln something to the power of something, well, here it's to the power of 4, and here is ln something to the power of 2x. So the indices can move down to the front. So we'd have 4 ln x plus 2x ln e. And remember, ln e is 1, so that there, ln e will just disappear, leaving you with 2x. From there, don't forget, you've already done quite a few steps, but you still need to differentiate. So dy by dx would be 4 times ln x goes to 1 over x, and 2x would become 2. So you'd end up with your answer. With this example here, we were having to apply this log rule. We've got ln something divided by ln something, so we can split it up with ln x take away ln 2x take away 1. Once we've done that, well, we can differentiate this here. ln x goes to 1 over x. Take away would stay as take away, and ln something goes to 1 over something. So ln 2x plus 1 goes to 1 over 2x plus 1. But you need to remember to multiply by the derivative of what's in the bracket, so we're multiplying by 2. It's the chain rule. From there, we'd have 2 over 2x plus 1. After that, really you should leave your answer in as a single fraction in its simplest form, so we need the same denominator. Multiply the top and the bottom here by 2x plus 1, top and the bottom here by x. That'll give us the same denominator. After that, we can subtract the numerators and just simplify that for your answer. With this one here, once again, we're having to apply log rules. We can see that we've got a square root. First of all, square root would be a fractional index. Joseph, it would be perfect, to the power of 1/2. And after that, Mary, what can you do? Brilliant, you can move the half down. So if you move the half to the front here, that's the same as half ln 2x cubed plus 1. After that, well, you're thinking half would stay as it is. ln something goes to 1 over something, but multiply by the derivative of what is in the brackets. Work your way through that and you will get your answer. Once we finished with ln x, we moved on to look at higher derivatives. And higher derivatives are basically when you differentiate again and again and again and again and again and again. What you need to do is, if you have y equals f of x, you can differentiate to get dy by dx, or f dash x. If you differentiate the first derivative, you get the second derivative, which is d with a b2y plus dx with a b2, but the way you read it is not with a b2. The way you read it is d2y by dx squared. And you can also write it as f double dash x or f dash dash x if you're differentiating f dash x. If you differentiate the second derivative, that'll give you the third. So you'd have f triple dash x or f with a wee 3x. Or if you differentiate d2y by dx squared, you'd get d3y by dx cubed. We did a few examples with that, really finding the fifth derivative. It's just showing you that you can differentiate again and again and again and again and again. Woo! Just for fun. So if you've got y, you can differentiate. You can get dy by dx. Differentiate that the way you normally do. Differentiate the first derivative, gives you d2y by dx squared. Second derivative. Differentiate this, you get the third derivative, d3y by dx cubed. You get the idea. Fourth derivative, fifth derivative. We went on again to look at working out the likes of the second derivative, but again bringing in our old friend, the product rule. How are you, product rule? I'm fine. So you've got y equals u times v, dy by dx is u dash v plus uv dash. Here is e to the x times cos x. So you've got u times v. It's one function in terms of x times another function in terms of x. Differentiate e to the x, differentiate cos x, and again you're applying the product rule. From there, what you need to do is you could always differentiate this part here by using the product rule on the first part, and then take away and use the product rule on the second part. But if you take out a common factor, the way I've done here, that means you've just got one function in terms of x times another function in terms of x. So you can then again apply the product rule to get the second derivative. So e to the power of x would be u, cos x take away sin x would be v, work out u dash, work out v dash, and then from there you would have u dash v plus uv dash. Multiply it out, take out any common factors, simplify it, just get down to your answer. What was the whole point in doing this? Stop right there. Well, the whole point in doing that is there are applications for the likes of the second derivative. One of them is it can be used to determine the nature of stationary points. If you have a stationary point and you then work out d2y by dx squared and you get something bigger than 0, it means the point is a minimum. If you work out d2y by dx squared at a stationary point and it works out to be less than 0, it means the stationary point is a maximum. If d2y by dx squared works out to be 0, it could indicate a point of inflection, but it could also mean a maximum or a minimum, so you'd have to use a nature table to determine which. However, we do look at that in a little more depth in chapter 8, looking at functions and graphs, and we also look at it in the likes of further differentiation or further calculus, because it can also be used to look at displacement, velocity, and then acceleration. Acceleration is found with the second derivative of displacement. So, after that, we then looked at inverse trig functions, differentiating Cos, sine, tan, sec, cosec, and cot is something we have already done, but we can also differentiate inverse trig functions. So if we have, for example, sine to the minus 1 of x, if you differentiate that, you get 1 over the square root of 1 minus x squared. Differentiate cos to the minus 1 of x would be negative 1 over the square root of 1 minus x squared. And differentiating tan to the minus 1 of x, you'd have 1 over x plus 1 squared. However, very important, you need to remember a lot of the time it's not just going to be x. It might be sine to the minus 1 of 3x or sine to the minus 1 of 7x plus 7. You'd have to apply the chain rule. So applying the chain rule with some examples, if we have sine to the minus 1 of 3x, well, sine to the minus 1 of something goes to 1 over the square root of 1 minus the something squared. So we'd have 1 over the square root of 1 minus the something squared. Here the something is the 3x. However, you need to multiply by the derivative of what is in the brackets. If you differentiate 3x, you get 3. So you'd multiply by 3. Perfect, which is why you get down to this answer. And obviously, if you've got 3x in brackets squared, you would just square that to get 9x squared. There are quite a few examples on this. This second example, again, is cos to the minus 1 of 1 minus 2x. So again, you're thinking if I differentiate cos to the minus 1, this is on the formula sheet, but you would get negative 1 over the square root of this 1 minus whatever x is squared. Here, the value of x is cos to the minus 1 of 1 minus 2x. So you'd have 1 minus 2x in brackets squared, which is what we have here. But again, think the chain rule. The chain rule is when you multiply by the derivative of what's in the brackets. So we're multiplying by negative 2. If you multiply by negative 2, well, the 2 negatives will cancel out and it'll give you a 2 here. Multiply out the brackets on the bottom, then you're thinking, well, I've got a 4 here and a 4 here. I could take out 4x, but if you take 4x out as a common factor, you're stuck. So take out just the 4. If you take out the 4, well, it means you can split it up into root 4 times root something. And you're doing that because you know the square root of 4 is 2. And then the 2 at the top and the bottom will cancel. Look back to the individual lesson if you are wanting me to go over this in more depth. You also get the likes of the harder examples. Once again, you've got a function in terms of x times another function in terms of x. So Tara, we use, you got it, the product rule. We've got the square root of 1 minus x squared times cos to the minus 1 of x. So we can work out u dash, we can work out v dash, and then again apply the product rule. This is a harder example. Look back to the individual lesson if you're wanting this in more detail. All I'm doing here is I'm pointing out that you can get harder examples like this and you need to know how to use them. Make sure this is something that you haven't forgotten. From there, we then looked at implicit differentiation. What on earth is implicit differentiation? Well, if I gave you x squared plus y squared equals 1 and asked you to differentiate it, you would really go down the route of rearranging that so you get y equals. If you have y equals, and then you've got on the other side x's, then it means y is defined explicitly in terms of x. However, if you just left it as x squared plus y squared equals 1, you've got x's and y's on the same side. And you would say that y is defined implicitly in terms of x. So explicitly is when you get y equals, and if it's all just mushed together, you would get y implicitly. So you get x's and y's on the same side. It is often difficult to rearrange your function to express it in terms, to express y explicitly in terms of x. So we need another way to differentiate, and you can do that. We could just differentiate just like this, because we know if we differentiate x squared with respect to x, you get 2x. You can easily differentiate 1 with respect to x, you just get 0. But we need to know how you would differentiate y squared with respect to x. So we can do that. And the way you would differentiate y is you would differentiate with respect to x by imagining it's an x. So imagine that as x squared, and if you differentiate x squared with respect to x, you get 2x. So if we differentiate y squared, we'd get 2y. But what you need to do is you need to think, well, I've differentiated y with respect to x. So you need to bring in dy by dx. You multiply that by dy by dx. You're really using the chain rule there. So if you differentiate y with respect to x, you'd bring in this dy by dx. Similarly, if you have y cubed, differentiate that, you get 3y squared, but multiply by dy by dx. Sine y, differentiate sine to get cos, so it'll be cos y, but bring in dy by dx. If you differentiate e to the power of y, that'll still be e to the power of y, the same as differentiating e to the x would stay as e to the x, but you multiply by dy by dx because we're differentiating y with respect to x. The same, ln y would go to 1 over. but you'd multiply by dy by dx. We did quite a few examples with this, and it's the same if you're using the product rule. Here, the product rule, you've got x times y squared, so u is x and v is y squared. Differentiate x with respect to x, you get 1, but if you differentiate your y with respect to x, differentiate y squared with respect to x, you get 2y, but because we're differentiating y with respect to x, you bring in dy by dx. From there then, if you differentiate with respect to x, the x times y squared, you would use the product rule, so u dash times v plus u times v dash. If you do that, x times 2y dy by dx, you tend to put numbers first, so put the 2 first, then put it alphabetically, you've got an x and a y, so put x and then y, and then put dy by dx on the end. It's the same here if you get x squared times cos y, again you're differentiating with respect to x. Differentiate y with respect to x, bring in dy by dx. Product rule, derivative then of what we were asked would be u dash v plus uv dash. Obviously the plus would become a minus because we've got positive and negative. What's the whole point in doing that? Well, we can get expressions for dy by dx. So the first real example with that lesson was to get your expression for dy by dx given x squared plus y squared equals 4. Differentiating x squared with respect to x, you get 2x. Differentiating y squared with respect to x, you get 2y. But you multiply by dy by dx because we're differentiating y with respect to x. Differentiate 4 with respect to x, you get 0. From there then, you can rearrange your equation. Every term divides by 2, so I'm doing that. Rearrange, so I get dy by dx equals. And we have our expression for dy by dx. We did more examples, but note here we've got x times y because we've got a product. We've got one function times another function, so we have to use the product rule. We have x times y, so u is going to be x, v is going to be y. Differentiate them both with respect to x, and then x squared would become 2x. But if you differentiate xy, you'd have u dash v, so 1 times y, which is y, plus x times dy by dx, which is x dy by dx. Again, the same thing, you need to rearrange, so you get dy by dx. So subtract 2x and y from both sides, and then divide both sides by x. So you get dy by dx equals. That was implicit differentiation 1. Implicit differentiation 2 is when we apply that to work out the equation of a tangent. We already know from higher, a tangent is a straight line, and to get the equation of a straight line, we need to think gradient point equation. Get the gradient of the tangent by differentiating the equation of your curve. So we differentiate the equation. We can then substitute in our x value, or in this case, we can sub in the point to get the gradient at that point. And then after that, we'll know the point, we'll know the gradient, so think gradient point equation. Y minus b equals m bracket x minus a. And as I said, this lesson was just all about using implicit differentiation to do that. With example 1, a curve is defined by the implicit equation. Find the equation of the tangent to the curve at 3, 4. So straight away you're thinking it's an implicit equation, so I'm using implicit differentiation. So we're not rearranging it, we're just differentiating as is. So differentiate x squared, it goes to 2x. Differentiate y squared, we're differentiating y with respect to x. So we'd have 2y times dy by dx. Differentiate 2x, it goes to 2. Differentiate negative 4y, it goes to negative 4. But again, we're bringing in dy by dx, people, because we're differentiating y with respect to x. From there, you could divide every term by 2, so do that. It gives us easier numbers. Leave any term with dy by dx on the left-hand side, but subtract x from both sides, subtract 1 from both sides. So it gives us the dy by dx terms on the left and every other term on the right. Take out dy by dx as a common factor. Woo! And if you do that, you'd have dy by dx times y take away 2. And then you can divide both sides by y take away 2, and you will get an equation for dy by dx. And remember, what does dy by dx show you? The gradient. Perfect, it gives you the gradient. We know we're wanting to get the equation of the tangent at the point 3, 4. So if we sub in x to be 3 and y to be 4, we'll get the gradient of that curve. Sub that into dy by dx, you get the gradient to be negative 2. From there, you know that the gradient of the tangent is going to be negative 2. We know the point is 3, 4, so we can use y minus b equals m bracket x minus a, and that will give us the equation of the tangent. After that, implicit differentiation 3, we looked at the second derivative. Why are we doing the second derivative? Well, Working out the first derivative is dead easy. We can do that easily enough. Working out the second derivative is something that we can apply later on when we're having to look at possibly acceleration, or if we're having to look at, instead of a nature table, the nature of stationary points. So working out the second derivative is something we have to be able to do. And with this equation here, f of x is defined implicitly by that equation, so we can easily differentiate to get the first derivative. So differentiate y squared with respect to x, we'd have 2y times dy by dx. Differentiate x squared, we get take away 2x. Differentiate 4, you get 0. That will give you then, if you divide everything by 2, y times dy by dx, take away x equals 0. You need to, for the first derivative, get dy by dx equals. So we're rearranging that, and that is what we are getting. What we then have to do is get the second derivative. So to get the second derivative, we're differentiating this first derivative. However, if you look at that, what we're going to do is we'd have to use the quotient rule. So u dash v minus uv dash over v squared. However, if you do that, because if you differentiate dy by dx, you would get 1 dy by dx. But that will then give us, if we stick it into the quotient rule, fractions within fractions, and it becomes very messy. What's easier to do is if we go back to this line before we had our fraction and just differentiate that. Both would work, but this is possibly slightly easier. If you want to try it the other way, go for it. See if you get the same answer. You will, or you should. Y dy by dx take away x equals 0. Here though, you've got y times dy by dx, so it's one function times another. It's a derivative here. So we've got y, u is going to be y, v is going to be dy by dx. If you differentiate y, you would get dy by dx, because differentiating y with respect to x will go to 1, but you're multiplying by dy by dx. And if you differentiate dy by dx, well, that's just giving you the second derivative. Differentiating the first derivative gives you the second. From there, u dash v plus uv dash, just using the product rule, will give you dy by dx times dy by dx plus y times dy by dx squared, and take away x would differentiate to be take away 1. From there, if you remember, on the last page, you worked out dy by dx. dy by dx worked out to be y x over y. So we can replace dy by dx with x over y. So it becomes x over y, as you can see here, times x over y plus, and then just leave the rest of it as it is. From there then, you've got x over y times x over y, which is x squared over y squared. You'd still have plus y times dy by dx squared, take away 1. After that, well, I would multiply everything by y squared to get rid of that fraction. So multiply this by y squared to leave me with x squared. Multiply this by y squared to give me y cubed, d2y by dx squared, and multiply the 1 by y squared as well. And really you should multiply the 0, but if you do that, it will stay as 0. From there, you can get to y by dx squared by leaving that to the left, subtracting the other terms without d2y by dx squared. So take away x squared from both sides, but add y squared to both sides, and that will give you this. And then divide everything by y cubed, and that will be your answer. After that, lesson 12 is looking at logarithmic differentiation. What's logarithmic differentiation? Well, it's used to find the derivative of a function, and we use it really when we have x as part of an index, or if we have a product or quotient of powers or roots. It makes it a lot easier to differentiate. How do we use it? Well, we take the natural logs of both sides, and then sometimes we would have to apply our log rules before we differentiate. Take this example here, we've got y equals 2 to the power of 3x. Note here we'd use logarithmic differentiation. Mohammed, why? Brilliant, because x is an index. If it's an index, we need to bring it down, and we bring it down by using logs. So use natural logs, it's all we really use in advanced higher. Take natural logs of both sides, so y will go to ln y. 2 to the power of 3x will go to ln 2 to the power of 3x. After that, the point in doing that is we can bring this 3x down. Whee! Bring that to the front. And then after that, you can differentiate. Differentiate ln y, it goes to 1 over y. But note, you're differentiating y with respect to x, so you'd have dy by dx. Differentiate 3x ln 2. Well, 3 is a number. ln 2, if you type it into your calculator, is also just a number. So the numbers will stay as they are. 3 stays, ln 2 stays. And if you differentiate x, well, that just goes to 1. So really the x will disappear. As I'm saying here, ln 2 is just a number. Treat this the way you would differentiate 7x. You're just left with 7. Or 19x, you're just left with 19. So 3 ln 2x would stay as 3 ln 2. From there, you want to get dy by dx on its own, so multiply both sides by y to get rid of this divide by y. That'll give us y times 3 ln 2. And then from there, well, we want to write our answer in terms of x, but note we've got a y. So how do we get rid of y? Because I gotta. Well, we get rid of y by multiplying or by swapping y with 2 to the power of 3x. So y becomes 2 to the power of 3x, and we would have 3 ln 2 times this y, which is 2 to the power of 3x. So that'll be your answer. We did other examples. This one here, note how we've got a product and quotient of powers and roots. It's quite confusing and it'll be difficult to differentiate. However, we can use logarithmic differentiation to make it quite easy. So if you differentiate this, well, you're thinking, oh, nightmare. Let's take the logs of both sides. If you take the logs of both sides, well, that'll give you ln y equals ln, the x squared e to the power of x squared, and then this is sine to the power of a half. So we'd have ln that. But you can apply then your log rules because you've got something times something. You can write that as ln x plus ln e to the power of x squared. And because you're dividing by sine x to the half, you can take away ln sine x to the half. So it's using your log rules. Look back at the lesson if you want it in a bit more detail. Differentiate from there after you bring the powers down. So bring the x squared to the front, bring the half down to the front. And then if you differentiate ln y, you just get 1 over y, dy by dx. Ln x goes to 1 over x. X squared goes to 2x. If you differentiate here, you'd have take away a half, it would stay. Ln something goes to 1 over something, so that would go to 1 over sine x. But remember your chain rule. The chain rule, the chain rule. Multiply by the derivative of what's in the brackets. Differentiate sine x, you get cos x, so you'd multiply by that. And remember, cos over sine is equal to cot. You got it. dy by dx, get that and so on by multiplying both sides by y. If you multiply both sides by y, you'd have y times all of this funkiness here. So it's y times all of that. Put it in brackets. And again, you're thinking you want dy by dx in terms of x, but you've got a y here. What is y equal to? Look at the question. Exactly, look at the question. You can see y is equal to all of this. So you're swapping y with all of that fraction at the start. After that, we looked at parametric differentiation. Parametric differentiation, what is that? Well, often you will have two variables, x and y, and they may be written in terms of a third variable, which is known as a parameter. A lot of the time, this parameter will be t, which will stand for time, or it may be theta. So if you imagine a rocket, imagine the rocket is on your coordinate grid and it's going to be firing. The x value and the y value will change with respect to t. So depending on the time, the x and the y value will change. It will be in a different position after 1 second, 2 seconds, 3 seconds, 4 seconds. So x and y are changing depending on what t is. So x is dependent on t and y is dependent on t. If t was 3, well, you would be able to work out the coordinates. You'd be able to work out x and y. If x and y are written in terms of t, well, to work out dy by dx, what you do is you use this formula here. dy by dx equals dy by dt, so differentiate y with respect to t. Then you would differentiate dx by dt and you would divide. So dy by dt equals dy by dx equals dy by dt over dx by dt. Some examples there. Here we've got x and y, both of them written in terms of t. To get dy by dx equals dy by dt over dx by dt. So differentiate x with respect to t, well, that's just going to give you 2t. Differentiate y, so dy, with respect to t, and the other side is t, so dy by dt would just be 2. dy by dx equals dy by dt over dx by dt, so we'd have 2 over 2t. Cancel the 2 at the top and the bottom, and you'd get 1 over t. We had harder examples. This one here, we've got x equals t over 1 plus t and y equals 1 plus t over 1 minus t. To get dy by dx again, you're thinking it's dy by dt by dx by dt. From there, you need to differentiate x with respect to t. But what would you have to use, Matthew? Yes, you would, because you've got one function in terms of x times in terms of t divided by another function in terms of t. You would have to use the quotient rule. So u dash v minus uv dash over v squared. So u would be t, u dash would be 1, v would be 1 plus t, v dash would be 1, u dash v minus uv dash over v squared. Simplify that, do the same for y. It's one function in terms of t divided by another function in terms of t. So, quotient rule again. U is on the top, v is on the bottom, differentiate, sub it into the quotient rule, and you'll get dy by dt. From there, to work out dy by dx, well, that's just dy by dt, which will be this, divided by dx by dt, which will be this. So you would end up with those two fractions, as I said, one fraction divided by another. Remember to divide fractions. Well, really what you're doing is you're taking this fraction here and you're dividing it by the other fraction. But remember, to divide by a fraction, you turn the other fraction upside down and you multiply. So 1 over the 1 plus t squared, flip it upside down and you get 1 over t, 1 plus t squared over 1. And the divide will become a times, which is represented here by the dot. From there, well, the 2 is staying as it is. You'd have 1 plus t all squared, 1 minus t all squared. You square on the top, square on the bottom, so just put brackets around the top and the bottom and put the squared outside. And that will be your answer. From there, we applied our parametric differentiation to look at the equation of a tangent. Yeah, we did. And just remember, from higher, the equation of a tangent, tangent's a straight line. To get the equation of a straight line, you're thinking gradient point equation. The gradient you can find by differentiating your equation. Once you differentiate, you can sub in the point, sub in the x value really that you did in higher, but here you need the point, sub the point in order to get the gradient at that point. If you know the point, you then know the gradient, and you can sub that into y minus b equals m bracket x minus a. Okay. We worked through some examples. Parametric equations here, we had x equals and y equals. We wanted to find the equation of the tangent to the curve at the point with parameter t equals 2. So we're differentiating x and y. Differentiate x with respect to t because it's written in terms of t. Differentiate y with respect to t because it's written in terms of t. Let's multiply the brackets first, makes it easy to differentiate. dy by dx equals dy by dt by dx by dt. So you can easily get dy by dx. From there, once you know dy by dx, well, dy by dx is your gradient. You can get the gradient then when t equals 2 by replacing t with 2. So that's what you do. First of all, replace t with 2 and you get the gradient. In this example, it's 13 over 4. We need to know the gradient point equation though. So gradient is 13 over 4. The point, well, we know t is 2. And how do we get x and y? Well, we were told at the start x equals t squared plus 1 and y equals t bracket t squared plus 1. So when t is 2, replace t with 2 in x and y, and we will get x to be 5 and y to be 10, which will give us that point. After that, the equation, gradient point equation, we know the gradient, we know the point, so we can sub that into y minus b equals m bracket x minus a. Okay, and you will get your answer. Third lesson on parametric differentiation was looking at second derivatives. To get the second derivative, really you want to work through that the same way you normally would to get a second derivative. However, because dy by dx will be written in terms of t, you would differentiate that with respect to t, but then what you need to do is you need to multiply that by dt by dx. Really, you're applying the chain rule there. So you'd have x and y both written in terms of t. Find an expression for dy by dx and d2y by dx squared. So dy by dx, just the way we were doing in the other examples. Look back to those lessons if you are unsure. But really you've got x in terms of t, y in terms of t, work out dx by dt, work out dy by dt, and then dy by dx, dy by dt by dx by dt. So you'd have 2t, 2 over 2t, which is 1 over t. So you're getting the first derivative the way you normally would. To get the second derivative though, what you do is, to get the second derivative, if you look here, you differentiate with respect to t, dy by dx. So let's do that first of all. So differentiating, that's this part here. So we're differentiating dy by dx with respect to t. So doing that, you differentiate with respect to t. Dy by dx was 1 over t, so we're differentiating 1 over t. Write that as t to the power of negative 1, if you move that up. And if you differentiate it, bring the power down, take 1 off the power, you get negative t to the negative 2, and write it with a positive index, negative 1 over t squared. So we've differentiated dy by dx with respect to t. But what we then need to do is think about the chain rule, and that is when, if you have the parametric differentiation, you would multiply by dt by dx. But note, dt by dx is really just whatever dx by dt was upside down. So going back a page for a second, dx by dt was 2t. That's 2t over 1, you can imagine it. So dt by dx is just 1 over 2t. So you're just wanting to flip dx by dt. So that's 1 over 2t. So that's what dt by dx is. That's what the derivative of dy by dx is with respect to t. So you then just multiply both of those parts together and you will get your answer for d2y by dx squared. Always remember, when it's parametric differentiation, you need to multiply by dt by dx. Final lesson in this chapter was parametric differentiation 4. We were looking at objects in motion. And the position of a moving particle, if that is given by parametric equations, so x will be a function in terms of t and y will be another function in terms of t. You can work out the velocity, the horizontal velocity, is given by differentiating x with respect to t. The vertical velocity is given by differentiating y with respect to t. So we've got dx by dt, which is horizontal, and dy by dt, which is vertical. You can work out the speed, and the way you do that is you think about Pythagoras. Really, to work out the speed, well, that's the square root of dx by dt squared plus dy by dt squared, and that'll give you the instantaneous speed of the particle. Working out an example, well, here you've got the position of a baseball. It's given by x equals 6t and y equals 45t minus 4t squared. Dx by dt, if you differentiate x with respect to t, you get 6. Differentiate y with respect to t, you get 45 minus 8t. From there, to get the instantaneous speed of the baseball, you sub it into the square root of dx by dt squared plus dy by dt squared. So from there, you'd have the square root of that 6 squared plus dy by dt squared will be 45 take away 8t all squared. From there, you could multiply the brackets, simplify all that, but you know t is 7, so just replace t with 7. So you'd have 6 squared plus, and then in brackets 45 minus 8 times 7 all squared. From there, you can work that out, and that gives you the square root of 157. If you did go to a decimal, a couple of decimal places, it'd be 12.53 units per second, but you're best leaving your exact values, so you should really leave it as the square root of 157 units per second. There was another example there with working out the instantaneous speed. Have a look at that if you're still unsure. But that is really it for the review lesson on differentiation. It has been quite long, but there have been 16 lessons in there. There's a lot to know for differentiation. Best of luck. Any problems, let me know. Bye.